Good morning, everyone. So today in this class, we are going to discuss about the refraction phenomena and the total internal reflections and refraction through a glass slab. So all the things we are going to cover in this class. So kindly listen to it to the full. Refraction. See, when a light ray travels from one transparent medium to the other, it deviates from its original path. This phenomena is generally called as refraction. This bending of light is happening because of the change in speed of the light in different medium. Because we know well, light may travel at different speed in different medium. So it travel at the most possible speed in empty space, which is equal to c equal to 3 into 10 to the power 8 meter by second. So light travels at this much of speed in empty space. But when the same light is traveling in glass medium or in water medium, its speed will be drastically reduced. It is because of the reduction in speed, the light ray will generally undergo the bending effect. So that bending effect is indirectly linked to the reduction of speed. So if the speed got reduced drastically in a particular medium, in that particular medium, the light ray will undergoes more bending effect. Okay, so just like a reflection principle, we have a refraction principle also. Based on the refraction principles only, all the lenses, all the transparent mediums are working. So we have two statement in the laws of reflection. The first statement tells you that just consider the two medium. Let's say that it's a air medium, it's a water medium. We can imagine light rays entering from air medium to the glass medium. As I already told you before, when this light ray is entering from one transparent medium to the other medium, its path will change. That path change is happening because of the reduction in speed or because of the enhancement of the speed. So let's say that here we can easily assume, let's say that the light ray might have gone like this originally if the second medium is also air means, but its path is going to change like this. Okay, we can call this ray as a incident ray, it's a refracted ray. Okay, and it's a normal line to the interface. Okay, so here we can define the two statement here. The first statement tells you that incident ray, refracted ray and normal line, all the three lines can be confined to the same plane. This is the first statement of the laws of refraction. The second statement tells you that it gives you the quantitative relationship between the incident ray and refracted ray. Let's say that this incident ray is making some I angle to the normal line. Okay, this refracted ray is making some R angle to the normal line. The second statement of the laws of reflection gives you the kind of correlations between this I and R. So we can also call the second statement of this laws of refraction as Snell's law. That establishes the relationship between this incident angle and the refracted angle. We can say the Snell's law in the following way also. Sine of the incident angle divided by the sine of the refracted angle is equal to the refracted index of the second medium to the refracted index of the first medium. I am considering this water medium as the second medium and air medium as the first medium. Yes, from the air medium to the water medium only the light ray is propagating. So that's why I coin the numbers in such a way. So this statement is called as Snell's law. The refractive index is nothing but it's a way of comparing the speed of the light in empty space with the speed of the light in that particular medium. For example, refractive index of the diamond is nothing but speed of the light in empty space divided by the speed of the light in the diamond. The ratio of these two quantities is generally called as refractive index of the diamond. So from these expressions we can very clearly understand one remarkable fact. If the speed of the light is drastically reduced in diamond, okay, if this value is very lesser, okay, then obviously the refractive index of the diamond is going to be more. So from this relationship itself we can establish a very clear-cut relationship between the speed of the light in a medium and refractive index of that particular medium. If the speed of the light in a particular medium is drastically reduced means that medium is supposed to be having more refractive index. Okay, so the diamond is said to be having more refractive index. Similarly, the air is said to be having a least refractive index because it's very closer to the vacuum. Okay, so for most of the practical purposes, we can treat the refractive index of the air as 1 itself. But technically, it should be a 1.003. We can assume that as 1. Okay, because we know that the refractive index of the air is nothing but refractive index of the air is equal to speed of the light in empty space by speed of the light in air medium. So we know very clearly the light travels at 3 into 10 to the power 8 meter per second in empty space. It nearly travels at the same speed in air medium also. So that will cancel off the terms on the numerator and terms on the denominator. So it leads to the 1. Okay. Okay, now I will tell you one more important thing about the refraction. So if a light ray is traveling from a rarer medium, rarer in the sense I am not talking about the denser medium or less denser medium. So here we are talking about the optical density. If it travels very slowly in a particular medium, that particular medium is said to be having more optical density. If light is traveling at very closer to the speed of the light in empty space, then that medium is said to be optically rarer. Okay, so now consider this case. Here we have a air medium, here we have a water medium. Air is rarer medium, water is denser medium. Okay, if a light ray is traveling from rarer medium to the denser medium, it will bend toward the normal line. Remember this. Originally, its path might be looks like this, but see, since the medium got changed at the interface, the light ray will undergo the bending effect, and that bending is happening towards the normal. If the light ray is entering from rarer to the denser means. The vice versa is also true. If the light ray is traveling from denser medium to the rarer medium means, it will bend away from the normal. I will draw that too. Imagine this is the air medium, it's a water medium. This time the light ray is going to enter from the denser medium to the rarer medium. So it's the angle of incidence. Okay, if the entire region is filled with water, the light ray might have traveled like this. But we have the air beyond a certain level, so obviously the light ray is undergoing the shift in speed. So it is because of the shift in speed, it will undergo the bending effect also. So here the light ray is entering from water medium to the air medium, so it will bend away from the normal. So it's the incident ray, it's a refracted ray. So it's an incident angle, it's a refracted angle. So again we can establish the mathematical relationship between the incident angle and the refracted angle through the Snell's law, which tells you that sin I by sin r equal to n2 by n1. Here n2 is air, n1 is n water. Okay, I suppose that you can able to understand these ideas very clearly, right? Okay, once if you got this idea very clearly, then we can discuss few more ideas also. There's one more important part I just want to establish here. Even though we may have a same glass medium, right, the different colors of light may travel in the glass medium at different speeds. So which tells you that the refractive index of the medium is somehow related to the wavelength of the light. That relationship can be given by the Cauchy's formula. So the refractive index of the light and the wavelength of the lights are related in this way, in this fashion. You can tell very clearly here the refractive index is inversely related to the square of the wavelength. So if you are sending some red color light, okay, through a glass slab, the red light is having more wavelength, so its refractive index is going to be lesser than over there. So if it is having lesser refractive index, it will not undergo that much of bending effect. So if you send a red color light to pass through the rectangular glass slab or some kind of a transparent medium, there its speed will not get reduced drastically. But if you try to send the blue color light, which is having a lesser wavelength, right? So when the lambda value is very lesser, the refractive index is going to be more. So obviously the speed of the violet light or blue light will get drastically reduced when it is traveling in the glass medium or in the water medium. Okay. Now we can see the various relationship one by one. I will tell you the optical path length. Okay. After discussing that, we can go for the lateral shift formula. Imagine it's an empty space. Okay, it's a medium, it's empty space. It's some transparent medium. You can imagine it's a water medium, right? It's a water medium and it's empty space. Let's say that light travels some x distance in the water medium in some t time interval, right? If the same light is traveling for the same t time interval, okay, how much of distance it will be making is called as optical length or optical path length. Okay, if the same light is allowed to travel in the empty space for the same t time interval, how much of distance it will make is called as optical path length. I can relate the x and x dash through the following way. We know that gently distance is equal to speed into time. So here the speed is speed of light in water medium into t, right? Similarly, x dash can be written as, here it is traveling with the speed of c for the same time interval t. So we know the relationship between the c and v. What is that? Speed of the light in empty space by speed of the light in water medium is equal to refractive index of that particular medium. Okay. So I can replace that c with what? N into v. Okay. So if I substitute this over here, I will be getting x dash is equal to n into v into t. So n into vt is nothing but x. So I got x dash is equal to nx. So it is a relationship we have. So this distance is called as optical path length. Okay. So if the light is traveling some x distance in a medium in a certain time interval, and how long it will travel in the same time interval in an empty space, it's called as optical path length. So it is related to the x in this following way. Okay, I suppose that you can able to understand this relationship, right? Now we can move on to the lateral shift concepts also. Consider a rectangular slab over here. This rectangular glass slab is having the thickness of t. Okay, let me shed some light on the top of this rectangular glass slab. So it's the incoming light. So this incoming light is falling and it is reaching over here. At this point of instant, if I try to draw the normal line to the interface, the normal line is going to look like this. So this incoming light is making some eye angle to the normal. So as I told you before, this light ray is entering from air medium to the glass medium. So from the rarer medium to the denser medium, the light rays are entering. So obviously the light rays will undergo the bending effect. The light ray will bend toward the normal here. So comparatively speaking with I, the R value is going to be somewhat smaller. Okay, and that's not the end actually, because the light rays are trying to enter from glass medium to the air medium once again. So whenever we have the change in medium, the light ray will undergo the bending effect one more time. Okay, at this point also, if you are at this point of instant, if you try to draw the normal line is going to look like this. Again here the angle of incidence is I. Okay, this time the light rays are entering from glass medium to the air medium. So obviously so from the denser medium to the rarer medium, if light enters, it should bend away from the normal. So the light rays are going to bend away from the normal. So let me call the final emergent angle as E, or if you wish you can call it as E. Okay. I can tell you that there is one more principle, it's called as principle of reversibility, and that tells you that if the path of the ray of light is reversed after suffering a number of refractions or reflections, it retraces its path. This principle is called as principle of reversibility. Just inverse the time, okay, just inverse the time. So this emergent ray is going to be an incident ray then. This incident ray is going to be the emergent ray then. Is it right? So obviously if this angle is I, then this angle also should be, this emergent angle also should be I. Because based on the symmetry we can tell that if this is R, this also should be R, because the alternate angles are equal. Okay, so if this is a R angle, this should be a R, and if this is I, this also should be I. So it is so clear that if there was no glass slab in this region, right? This original light ray might have traveled along this way. Sorry. If there was no glass slab, this original light ray might have traveled along this way. But now we can see very clearly this emergent ray is also traveling the same direction, but the position of the light rays are shifted laterally a little bit. So we can try to calculate that lateral shift through a very simple formula. Okay, by using the same Snell's law we can able to calculate the lateral shift. I will tell you the way to calculate that now. Imagine we can name the points now. Okay, let me call this point as a O. It's a O, and we can extend this line. This point of intersection is called as N1. Similarly, let me call this point as A. Okay, so our task is we want to establish the lateral shift distance, which means the perpendicular distance between the two parallel lines is called as lateral shift. I can call this lateral shift distance as AN2. So our task is we should find out this. Okay, how can we establish that? It is so clear that consider this OAN2 triangle. OAN2 triangle. Consider this OAN2 triangle. You can very clearly understand one thing. So this angle is I, okay, and so this angle is R. So this in between angle should be a I minus R. If this is the I minus R, right? So now I will draw the triangle alone separately so that you may have some very clear visibility. So this is the I minus R, and it's a O, it's a it's a N2. Okay, I can tell then sine of I minus R is equal to, if you consider this right angle triangle, it's going to be the opposite side, it's going to be the hypotenuse. So sine of I minus R is equal to opposite side is AN2, hypotenuse is OA. Let it be, and this OA can be replaced with what? You know that if you consider this OAN1 triangle, you can see very clearly the projections of the OA over this line is called as ON1. So OA cos R equal to ON1. This ON1 is nothing but the thickness of the glass slab. I can write then OA equal to ON1 by cos R. ON1 is nothing but the thickness of the glass slab. So in the place of OA I can substitute this. I'll be having like a sine of I minus R equal to AN2 by OA. OA can be replaced with T by cos R. Okay. Ultimately my task is I should get the AN2 only. So if I retain the AN2 alone on one side and bring all the parameter to the another side, I'll be having this AN2 equal to T into sine of I minus R by cos R. Okay, so I got an expression like this. So this is the formula we have for lateral shift. So whenever a light ray is passing through the rectangular glass slab, there will be no change in the path. It will be going the same direction only, but that light ray will be laterally shifted to the rightwards or leftwards by this much of distance. So if I value is very small, right? If I is very small, then obviously R will also be very smaller. Then the lateral shift formula can be modified into this following form. Since the R is very small, it's going to approach as the 0. You know that when the cos 0 value is equal to 1, because if the R tends to 0, the cos R tends to 1. So similarly, if I and R values are so smaller, the sine of I minus R can be replaced with I minus R itself, because sin theta can be approximate as theta for smaller angle. So I can replace the sine of I minus R with I minus R itself, and cos of R with a 1. Okay, so I got a final expression, lateral shift expression as T into I minus R. So we got these expressions. Now if you apply the Snell's law for this particular surface, what value you may have? You will be having like a sine of I by sine of R, which is equal to N2 by N1. Here N2 is N glass, N1 is N air. N air value is 1 literally. So for a smaller angle I can write sine I by sine R can be replaced with I by R itself. So I by R equal to Ng. N air value is 1. So I can write I equal to Ng into R. So I can try to replace this quantity over there. Okay. So T into I minus R, R can be replaced with what? R can be replaced with I by Ng. So R can be replaced with I by Ng. If I take the I as a common factor, I will be having like 1 minus 1 by Ng. So this should be the formula we have for lateral shift. I suppose that you can able to understand these derivations very clearly, right? Okay, once if you got this idea very clearly, then side by side we can also develop few more ideas related to this. Consider we have here air and water. Okay. From the free surface of the water at a certain depth, we have a fish. Let me say that the fish is our object, okay, and observer who is living on the air medium, he observed that fish. So to his eyes the fish may not be located here, it may be located at somewhat elevated location. So I think it's not a very complicated thing for you to understand, right? So when you are viewing the floor of the swimming pool, right, it seems to be very shallow, but when you actually enter into the swimming pool, it will be more deeper than it is visually appearing. So the same phenomena is going to happen here also. The fish is located originally at the O position, but with respect to this observer, its position will be uplifted to a certain level. So we are going to calculate that shift distances now. How can we calculate that? Imagine from the fish surface, okay, we can assume the two light rays. The one light ray is emerging out in this way, okay. At this point of incidence, if you draw the normal line, so this light ray is making the 0 angle of incidence, so its angle of refraction is also 0. From the surface of the fish, you can imagine one more light ray also, and this light ray on hitting on the interface, it will undergo the refraction effect. Since the light rays are entering from water medium to the air medium, okay, it will bend away from the normal. Okay, it will bend away from the normal. Okay, as far as this external observer is concerned, right, if he imaginarily extend this two light rays backwards, these two light rays seems to be meeting over here. So that's where he will perceive the fish. So that location can be called as image of the fish. Yes, it is not the actual position of the fish. Fish is actually located at somewhat deeper level. So, but to this outside observer, right, from this point only, these two light rays seems to be emerged out. So that's why he will perceive the fish over here. Okay, and you can see one thing here. Okay, if this angle is I, this angle also should be I, right? Because alternate angles are equal. Similarly, this angle is R, and this angle is also R. Okay, let me call this point as a. Okay, now consider various triangles now. Before considering anything else, I can write the Snell's law, which can relate the incident angle and refracted angle. So that tells us sin I by sin R equal to N2 by N1. N2 is air medium, N1 is water medium. So I can write for smaller angle, I can replace the I and sin I and sin R with the I and R itself. Okay. There's one more thing I think you might have studied from the high school mathematics. That tells you that for a smaller angle, the sin theta is approximately equal to the theta, and sin theta can also be approximately equal to the tan theta. For a smaller angle, all these three values are identical. So this sin I, sin R can be replaced with tan I and tan R for a smaller angle, of course we can make use of this approximation. Okay, the tan I can be consider this triangle, consider this OPA triangle or POA triangle. If you consider this POA triangle, you can very clearly say that tan I equal to opposite side is PA and adjacent side is OP. Similarly, if you consider PRA triangle, from there you can infer tan R equal to PA and adjacent side is IP, which is equal to N air by N water. This PA will get cancelled off. IP is nothing but image distance, OP is nothing but object distance. I can call this IP as a apparent depth or H dash and OPS real depth. The ratio of these two is equal to N air by N water. N air is 1 approximately, so N water will be having this. So I can simply write then H by N water is equal to H dash. So generally I can write H by refractive index of the medium equal to H dash. It's a relationship we got. So it's a real depth, it's apparent depth. Okay, I told you before, right? The water is having refractive index, its value is greater than 1. So obviously if you divide the actual depth with a number which is more than 1, that ratio is going to be a somewhat smaller one. So obviously the apparent depth is going to be a lesser one than the actual depth. We can also calculate the shift in distance. Okay, we can also calculate by how much of distance the fish may be uplifted. So we can call this distance as a shift distance. The shift can be calculated by using this formula: real depth minus apparent depth is called as shift. So we can write H minus H dash. H minus H dash can be replaced with what? H by refractive index of the medium. If I take the H as a common factor, I will be getting a 1 minus 1 by N medium. So which is equal to shift. It's a formula we got for the shift. Okay. Similarly, we can develop the similar kind of formulas for the other case also. Now consider this case. Again, you have a air medium, water medium, but this time the object is going to be a flying bird. So it's going to be our object. It's going to be a flying bird, and this flying bird is seen by the scuba diver, okay, from the water. So now this time observer in the denser medium, object in the rarer medium. So now we can again try to work out the similar kind of calculations one more time. This time the case is going to be different. Imagine from the flying bird, from the objects, okay, one light ray is approaching the observer. Since this light ray is making the zero angle of incidence, so it goes undeviated. We can assume, we can consider one more light ray also from the object, as this light ray is approaching the interface at a certain angle to the normal. After getting refracted, the refracted light ray is going to be very closer to the normal. So if you imaginally extend this line, these two light rays, okay, which was perceived by the observer, seems to be meeting over here. So that's where he will perceive the bird. So it's going to be the image location. It's going to be the image locations of the bird. Again, we can do the similar calculations. if this angle is I and this angle is also going to be I, okay. Similarly, if this angle is R and this angle is also going to be a R, and if you wish you can name them again. Let me call this point as a P and this point is a. Now consider the POA triangle. Consider POA triangle. From that you can infer that tan I is equal to PA by OP. Similarly, consider PIA triangle. You can relate that tan R equal to, what's the opposite side? PA. What's the adjacent side? IP. Okay. Again, one more time you can make use of the Snell's law here. If I make use of the Snell's law here at this interface, what value will be having? Sin I by sin R is equal to N2 by N1. Here the N2 is N water, N1 is N air. Okay. For a smaller angle, I can replace the sin angles with the tan angles. So the sin I sin R can be replaced with tan I by tan R, which is equal to N water by N air. N air is 1. So tan I tan R can be replaced with these quantities. I will be getting a PA by OP divided by PA by IP, which is equal to N water. The PA will get cancelled off. I got a IP by OP equal to N water. And IP is nothing but it's a image height, and OP is nothing but object height. So I can call this IP as a apparent height. It's a real height. So from this you can very clearly infer apparent height is equal to N water times of the real height. So the N water is going to be more than 1. So apparent height is going to be somewhat larger than the real height. So when a scuba diver is looking at the flying bird, its apparent height is going to be somewhat larger than the actual height. So that's what you can able to infer from this derivations. Again you can try to calculate the shift also for this case. So shift is equal to, what's the image height? Image height is PI, object height is OP. So PI minus PO, the difference is called a shift. So I can write PA is apparent height, right? Apparent height is equal to N water into real height. Let me call this apparent height as H dash, real height as a H. So I can write H dash is equal to N into H minus H. So if I take the H as a common, I'll be having like a N water minus 1, which is equal to the shift formula. If the transparent rectangular block is placed between the object and observer, okay, the portion of the object will be shifted rightwards or leftwards based on the refractive index value of the rectangular glass slab. I will try to calculate the exact value, exact length to which the portion of the object will be shifted. So by using the principle which we learned before, now consider this is the object. From the objects, one light rays are coming in this way. So at this point of instance, if I draw the normal line, so here the angle of incidence is 0, so angle of refraction is also 0. This light ray will goes undeviated, it will reach the observer eye. From the object I can consider one more light ray also, but at a certain angle, okay, at a certain arbitrary angle. At this point, if I try to draw the normal line, so to this normal line, this incident ray is making a certain angle. Let me call that angle as the eye. So since the light rays are entering from air to glass, its path will change. So the light ray will bend toward the normal, and it will go in this way, and it may hit on the another interface one more time. At this point, if I draw the normal one more time, So this time light rays are entering from glass medium to the air medium, so it should bend away from the normal. So if I imaginally extend these two light rays, okay, it appears to be coming from this point only. So that's where this observer will perceive the object. So which means if an object is being viewed through the rectangular glass slab, okay, and the object portion is being shifted towards the rectangular glass slab by a certain value, we can try to calculate this certain value through the mathematics. Okay, now consider rectangular glass slab. Here we have your object. Okay, if this object is being viewed by the observer who is living on the glass wall, then obviously we have learned the relationship between them, right? Because this time object is in the rarer medium, observer in the denser medium. Okay, observer in the denser medium. So when the observer from the denser medium is looking into the object, its apparent portion will be located at some distance away from its actual portion. So let's say that it's an image of these objects. Okay, we can call this as I dash. So let me call this original distance as here OP. So the original distance is OP, and the apparent portion is I dash P. Okay, we know the relationship between them. What is that? OP into refractiveness of the glass equal to IP, I dash P. We learned that thing right now only. We have seen the same thing from this example, scuba diver example. Yeah, we learned the thing from the scuba diver example, where we know the relationship between the H dash and H dash equal to H into N water. So I can make use of the same formula here. So I can say that OP into Ng equal to I dash P. So that's where he will perceive the image. If the whole world is made up of glass, okay, this is where object may appear to be located. But obviously the world is not made up of glass, so it's made up of air. So let's say that the world is made up of some glass medium with a thickness of T, whereas the observer is viewing from the air medium. See, if the entire thing is made up of glass, this is where the object may be located, right? If the entire thing is made up of glass, if the entire surrounding medium is made up of glass, this is where the object may be located. Okay, so now imagine the whole thing is made up of glass. If the whole thing is made up of glass, okay, this is where the object is located. So this time you can imagine object is located in the glass medium, so over here, and that object is being visualized by the observer who is living on the air. So this time object is in the denser medium, observer in the rarer medium. Again, you know the way to calculate that shift. So we know that apparent portion, actual portion of this object with respect to this observer, I can call this actual position, and its final image is forming over here. Let me call that as a V. I can say that U equal to what? U is equal to I dash P plus T. I can write the same as OP Ng plus T. OP Ng plus T. Similarly, the final portion, we know the relationship between these two. Okay, when the observer is in the rarer medium, object in the denser medium, we know the relationship between these two. U by Ng equal to V. So the final portion is equal to u by ng. U is OPNG plus P by NG. I'll be getting like OP plus T by NG, which is equal to V. So now imagine, so original portion of the object is, with respect to the observer, the original portion of the object is OP plus T. So OP plus T is the original portion of the object, and the finally formed image is located at this much of distance away from the observer. The shift can be calculated by subtracting these two. On subtracting these two, I'll be getting the shift. So I'll be getting like a T minus T by NG. If I take the T as a common factor, I'll be getting a 1 minus 1 by NG. This is the formula we have for shift. So any object, if it is observed through the rectangular glass slab, okay, and its position will be shifted towards the rectangular glass slab by this much. It's the most remarkable idea. You should be very familiar with this because we will be using this formula more often. Okay, and apart from that, in refraction we are having one more important subtopic. It's called as critical angle. We will discuss that idea also now. Imagine we have a optically rarer medium and optically denser medium here, and if I try to send the light ray from the denser medium to the rarer medium, okay, I have a limitations on that, because let me imagine this is the incident light. This incident light is making some eye angle to the normal line to the interface. So when these light rays are trying to propagate from the water to the air, it will bend away from the normal. Is it right? So comparatively speaking, with the eye, R value is more, and if I try to increase the angle of incidence more and more, the angle of refraction will also be increasing more and more. So at a particular value of the angle of incidence, the refraction value will become 90, which means the reflected light will start to gaze over the interface. So exactly at what angle of incidence this phenomenon is happening is called as critical angle. If I try to send the light ray exactly at the critical angle, the refracted light will start to gaze over the interface, and if the incident rays are having more angle than this critical angle, then they will no longer enter into the rarer medium. It will be completely reflected back into the same denser medium. So this phenomena is called as total internal reflection, and it is because of the total internal reflections only the dimensions are. It is because of the total internal reflections only the diamonds are shining actually, and we can extend this idea to understand this case also. Imagine we have a pond. Okay, from the surface of the pond at a certain depth h, we have a fish. Okay, and this fish is trying to see the surrounding world through a light which are coming from this circular disc. Yes, it cannot receive any more light ray from this ray area. I will tell you the reason for it. Imagine from the fish eye, we can imaginally draw a light ray, okay, and this light ray is reaching the interface at a critical angle. So obviously if the angle of incidence is critical angle, then refracted angle is going to be 90 degree. So if this is the C, it is going to be 90. So based on the critical angle, if you try to draw a figure, and it will construct a cone. If you place any bulb over here, through that circular disc only the light ray can emerge out, because in this part light ray cannot emerge out because it will be completely reflected back into the same medium. Yes, here the angle of incidence is more than critical angle. So obviously the light ray will get reflected back into the same medium. The area of this, we can try to calculate the area of the disc. Let me imagine this ring is having the radius of r, and obviously if this angle is C, this angle also C, right? So if you consider this right angle triangle, you can imagine tan C equal to opposite side is R, adjacent side is H. So for smaller angle approximation, we can say that sin I by sin R equal to N2 is N air, N1 is N water. So I'll be getting like a sin C equal to 1 by N water. Okay, and for a smaller angle, right, see the sin C can be rewritten with sin means opposite side is R, hypotenuse is root of R squared plus H squared. So which is equal to 1 by N water. So on simplifying this, I may have expressions like N water equal to R squared plus H squared root of by R. So if I square this on either side, I'll be getting a N square equal to R squared plus H squared by R squared. I'll be getting like 1 plus H squared by R squared. So it's the relationship we have. If the refractive index of the medium is N and the relationship between the H and R is this much. Okay. So the fish is located at the H depth and it can see the whole universe through this conical regions only, because the light rays from the entire universe will be reaching the fish through that circular disc only. So that's why this circular disc area is called as area of illumination. Okay, now we can work out some problems on this. Look into the first question now. We have a glass slab and it is having some thickness, we don't know. A ray of light takes 10 to the power minus 9 seconds to cross this. Okay. So a ray of light takes 10 to the power minus 9 seconds to cross this. So the thickness of the glass slab they are asking, let me call the thickness of the glass slab as x. You know the formula for x. Distance is equal to speed into time. So the glass slab is having the refractive index of 1.5. So I can say that speed of the light in that glass medium is nothing but speed of the light in empty space by refractive index. Okay, so V can be replaced with C by N into T. So I can replace the C with 3 into 10 to the power 8 and N with 1.5 and T with 10 to the power minus 9. So on cancelling of all the parameters and simplifying this, I'll be getting like a 2 into 10 to the power minus 1, which is 0.2 meter. So X should be a 0.2 meter. This question also similar to that. See, now look into the question number 5. So we have a block of glass, its thickness is 10 centimeter, its further side is silvered, so this side is silvered completely. A small object is placed 20 centimeter in front of the block of glass. So from here at 20 centimeter distance away, we placed an object. An image is formed at 22 centimeter behind the silvered glass. So the image of this object is going to be formed inside of the mirror at a distance of 22 centimeter away from the mirror surface. So the question is about find the refractive index of the glass. Imagine I told you before, if you view this mirror, right? If you view this mirror from the air medium, right? We already discussed this, right? A pond will appears to be shallow than its actual depth, right? The same logic can be applicable here also. So with respect to this outside observer, right, this silvered surfaces will not be appears to be here. It seems to be shifted and it seems to be uplifted in front. So it's apparent portion. Let me call this apparent portion as x. Okay. We know the total distance is 10. Total thickness of the glass slab is 10. So this distance would be a 10 minus x. So with respect to this outside observer, right? With respect to this outside observer, right? The bottom of the, the bottom in the sense, the right end of the silvered surfaces is going to be shifted leftwards by 10 minus x distance. So we can call this distance a shift. Okay. And so to this observer, right? To this observer, the silvered face is going to be here only. So from the object to the mirror, the distance is 20 plus x. Okay. From the mirror to the image also we can express the same distance. So if we use that logic, 10 minus x plus 22 should be equal to 20 plus x. On simplifying this, I'll be getting what? I'll be getting like a 2x is equal to 10 plus 22 minus 20. I'll be getting 12. 2x is equal to 12, x is equal to 6. If x is equal to 6, okay, then what's the shift value? So you know that shift is equal to what? 10 minus x. So 10 minus 6 is equal to 4. So we can readily use the shift formula then. Shift is equal to, we discussed the formula for the shift before, right? What is that? Here we have seen the shift formula. Yeah, this is the shift formula. Shift equal to h into 1 minus 1 by n medium. So make use of the same formula here. So the original depth is 10, 1 minus n medium. Shift value is 4. On simplifying this, I'll be getting like a 4 by 10 equal to 1 minus 1 by n. 1 by n equal to 1 minus 4 by 10. On simplifying this, I'll be getting like a 10 minus 4. It's a 6 by 10. So n equal to 10 by 6. I'll be getting like a 2 3s are 6, 5 2s are 3, 3 2s are 6, 5 2s are 10. So n equal to 5 by 3. So it should be the answer then. 5 by 3 in the sense 1.67. So n value should be equal to 1.67. That should be the answer then. Okay, look into the question number 6. A glass slab of thickness 4 centimeter. It's a glass slab of 4 centimeter contains the same number of waves as 5 centimeter of water. So now imagine it's a water. Its length is 5 centimeter. So the same number of waves is presenting on glass. It's a single wave. 2, 3. Let's say that here we have n number of waves. The n number of waves is presenting in the glass slab. The same n number of waves are presenting on the water is also. So let's say that each wave is having the wavelength of lambda. So the total length, the thickness, the t equal to what? N into lambda. So n into lambda 1. So which is equal to T1, the thickness of the glass slab. You know the thickness of the glass slab is 4 and n is the number of waves, lambda 1 is the wavelength of the light in the glass medium. Similarly, T2 equal to, it's a lambda 2, okay, and here also we have the same number of waves. So let me say that n into lambda 2 equal to T2, the thickness is 5 n into lambda 2. On cancelling of this, I'll be having like a 4 by 5 equal to lambda 1 by lambda 2, which is equal to, the formula for the lambda. So that for any wave, if you multiply the wavelength with frequency, you'll be getting the speed of the light or speed of the wave. So in that case, frequency is independent of the medium, so obviously there should be a proportional relationship between the lambda and v. So lambda 1 can be replaced with v1, lambda 2 can be replaced with v2, and v1 v2 are inversely related to the n1 and n2. So yes, we know that v equal to c by v, n equal to c by v. So v equal to c by n. So v1 by v2 equal to n2 by n1. So I got an expression like this. So refractance of the medium, right? They're asking refractance of the glass. They're asking, and they have given the refractance of the water as 4 by 3. So I consider water as the second medium. So I know the refractance of the water, n2 is equal to 4 by 3. Okay. So 4 by 5 equal to n2 by n1. n2 is 4 by 3, n1 is n1. So n1 is equal to 4 by 3 into 5 by 4. The 4 will get cancelled. I will be getting the 5 by 3 is the answer. So answer is option A. And look into the 7th question. I told you this fact is one of the most important fact. Whenever light rays are traveling from one transparent medium to the another transparent medium, when it is entering from one transparent medium to the other transparent medium, its wavelength will change, its speed will change, but its frequency will never change. The frequency of the light is independent of the medium. Okay, it's one of the most important thing you should be very familiar with. Okay, look into the question number 10 now. Okay, here we have a clean slab of ice. So it's ice slab, and its thickness is 1 meter. Its thickness is 1 meter. A ray of light falling at an angle of 37. And it is refracted into it at an angle of 37. A ray of light falling at an angle of 37 with the surface of the slab. So this angle is 37. So this should be equal to what? 53 degree. Okay, it's a incident angle. So when it got entered into the ice medium, so its path got changed into this way. This angle of refraction is 37 degree. So calculate the time taken by the light ray to cross the slab. So how long the light ray will take to cross the slab? It's a thing we have to calculate. And before doing that, you should know the refractive index of the glass slab, right? That data is not given anywhere, so you should know it. How can we get it? You can apply the Snell's law here. So sine I by sine R equal to n ice by n air. N air is equal to 1. So I can tell sine of 53 by sine of 37 is equal to n ice. We know the 3, 4, 5 triangle, right? We know the 3, 4, 5 triangle. So this it's a 3, it's a 4, it's a 5. This angle is 53 and this angle is 37. Okay, so sine of 53 is equal to what? It's simply 4 by 5. So it's simply 4 by 5. Sine of 37 is equal to 3 by 5. So the 5 will get cancelled off. So refractive index of the eyes is equal to 4 by 3. I got the refractive index of the light, refractive index of the eyes as 4 by 3. Once if I got that value, I can tell with what speed the light rays are traveling in the ice medium. We know that V ice is equal to speed of the light in empty space divided by speed of the light in ice medium. That ratio is called as refractive index of the ice. So speed of the light in ice medium is equal to speed of the light in empty space by refractive index of the ice. So it's a 3 into 10 to the power 8. It's a 4 by 3. I got what? 9 by 4 into 10 to the power 8 meter by second. So with this speed only the light rays are going to travel in that ice medium. Okay, and how much of distance it is making? We know that this distance is 1 meter. Okay. Okay. We know that cos 37. Look into the 3, 4, 5 triangle. Cos 37 is equal to 4 by 5. Is it right? So cos 37 is equal to 4 by 5. And consider this triangle, right angle triangle. Cos 37, it is nothing but if this distance is considered as A, so A cos 37 is equal to 1. So cos 37 equal to 1 by A. So cos 37 is equal to 4 by 5, which is equal to 1 by A. So A equal to 5 by 4. So we got this distance. So A equal to 5 by 4. So this light rays are traveling this much of distance with this much of speed. So the time taken is equal to distance by speed. Distance is equal to what? 5 by 4. Distance is equal to 5 by 4. Speed is equal to 9 by 4. The 4 will get cancelled off. I will be getting a 5 by 9 into 10 to the power minus 8 second. It should be the answer. It might have given wrongly in the options, but it should be the solution. Okay, now look into the question number 24. So a fish in water, the reflection of the water is N, looks at a bird vertically above in the air. I think we derived the expression for it, right? Observer is located inside of the denser medium, whereas the object is placed on the rarer medium. So if y is the height of the bird, okay, x is the depth of the fish from the surface, then the distance of the bird as estimated by the fish. You know that it's actual portion of the bird, but whereas its apparent portion is going to be shifted away from the fish. So it's image portion. And we know that we calculate the formula for this shift, right? We know the formula for this shift. I can tell that from our previous discussions, you should be already familiar with that. Yeah, in that case, shift equal to h into n water minus 1. So shift equal to h. So shift equal to h into n water minus 1. So shift is nothing but OI, right? So OI value is equal to this much. So in the question what they're asking the distance of the bird as estimated by the fish. So obviously with respect to the fish, okay, the bird is located at what distance away? it is located at x plus y plus OI. Okay, it's a portion of the bird with respect to the fish. I can say that x plus y plus here OI is nothing but, H is nothing but y itself. So on taking the y as a common factor, I will be getting like n minus 1 plus 1. So x plus y into n. This should be the portion of the fish, portion of the bird as estimated by the fish. So it should be the answer. Okay. Now look into the question number 26. It's not a breaker, it's a beaker. It's mistakenly given. Okay. So we have here a beaker containing water. So we have here a beaker containing water. It's a water. Its refractive index is equal to 4/3. Is placed on the glass slab. So this entire water column is placed on the glass slab of thickness 0.1 meter. And this glass slab is having the refractive index of 1.6. Scratch at the bottom of the glass. So here we have the scratch. Here we have the scratch at the bottom of the glass. It appears at the interface of the two media. So here we have a water, here we have a glass. So when an observer is looking at this scratch is appearing to be over here. Okay. So calculate the height of the water in the beaker. It's what we have to calculate. How can we get it? I can calculate this by using the shift formula again. If the total shift is equal to 0.1 meter, right? So because of the presence of the water medium as well as the glass medium, the scratch at the bottom of the glass slab is going to be shifted upwards. So the total shift is equal to 0.1 meter. I can able to calculate the total shift by summing up the individual shift. So let me assume we have the shift because of the presence of the glass medium alone. We can calculate that shift as a shift 1. Shift 1 is equal to, we know the formula for the shift. It is nothing but T into 1 minus 1 by n glass. So the thickness of the glass slab is 0.1, okay, 1 minus 1 by n, which is 1.6. It's a shift 1 we got, which means shift because of the presence of the glass slab we got. Okay. Similarly, shift because of the presence of the watery medium, I can call this a shift 2. So we don't know the height of the water column. Let me call the height of the water column as a h. It's unknown, that's what we have to calculate. So h into 1 minus 1 by n water. We know that the refractive index of the water is 4/3. It's very clearly given. So the total shift is equal to 0.1. So shift 1 plus shift 2, if you add this, that should manifest to 0.1 meter. So 0.1, 1 minus 1.6 plus h 1 minus 3/4 equal to 0.1. It's what we calculated now, right? So you try to simplify this further. I'll be getting like 1.6 minus 1, it's a 0.6 by 1.6. Similarly, 4 minus 3, it's a 1/4 is equal to 0.1. Okay. Just divide the whole thing with 0.1. I'll be getting of what? 0.6 by 1.6 h 1/4 into 0.1, 0.4, right, equal to on either side we should divide with the 0.1. So on this side we'll be having the 1. So on simplifying this, I can able to rewrite the same as 6/16 h 10h by 4 equal to 1. So what I got? I got a 10h by 4 equal to 1 minus 6 by 16. So 16 minus 6, it's a 10 by 16, it's a 10h by 4, the 10 will get cancelled off. I will be getting a h is equal to 4 by 16, which is equal to 1 by 4. So h value is equal to 0.25 meter. That should be the answer then. So the height of the water should be equal to 0.25 meter. This should be the answer. Now look into the question number 31. We have a small air bubble inside of a glass cube of side 15 centimeter. We have a glass cube. Okay, when it is viewed from the top, a bubble appears at a distance of 5 centimeter. So the apparent height of the bubble is 5 centimeter. When the bubble is being viewed from the top surface, when the same bubble is viewed from the bottom, it appears to be located at the 5 centimeter. Sorry, 7 centimeter. So we know the two apparent depth of the air bubble, and we know the side length of the cube also, it's a 15 centimeter. The question is about the refractiveness of the glass. Okay. We know very clearly the real depth is taken as a h. So h by refractiveness of the glass is equal to h apparent. Okay, it's a formula we have. So real depth of the air bubble equal to h dash into ng. Let we call the h dash as phi, ng is an unknown quantity, so it's a h real. So when we are viewing the air bubble from this side, okay, even though it may appears to be at a depth of 5 centimeter, it was originally at a depth of what? This much. It's a h real. So once if you got the h real, you can able to get the true depth from this side also, because we know that the true depth from this side is equal to 15 minus 5 ng. Is it right? So if you apply the same ideas from this side, we know the formula for it, right? We know the h real by n glass is equal to h apparent. H apparent is equal to 7. So h real is equal to 15 minus 5 ng divided by ng equal to 7. On simplifying this, you can able to get the ng value. So 15 by ng minus 5 equal to 7. So I'll be getting like a 15 by ng equal to 12. So ng equal to 15 by 12. On simplifying this, I'll be getting like 5 by 4. So 5 by 4 should be the answer. Now look into the question number 33. Light travels with the two velocities in different two medias. In the first media, it travels with the speed of 2 into 10 to the power 8. In the second medium, it is traveling at the speed of 2.5 into 10 to the power 8 meter per second. So in the first medium only, its speed is drastically reduced. So it should be a denser medium. So in the first medium, the speed is v1. Then in the second medium, the speed is v2. So in question, they are asking us to calculate the critical angle. We know the formula for the critical angle. Whenever the light rays are trying to travel from the denser medium to the rarer medium, if the angle of incidence is more than critical angle, it will start to reflect inside in the first medium itself. So that phenomenon is called as total internal reflections. So the angle of incidence at which the refracted angle will become equal to 90 is called as critical angle. So I can use Snell's law then, sine of IC by sine of 90 is equal to N2 by N1, or it's a V1 by V2. So V1 value I know it's a 2 into 10 to the power 8. V2 value I know it's a 2.5 into 10 to the power 8. 10 to the power 8, 10 to the power 8 will get cancelled off. I'll be getting a sine of IC equal to 2 by 2.5. Okay, so IC is equal to what? Sine inverse of 2 by 2.5, which can also be written as 4 by 5. It should be the critical angle. Okay, look into the question number 35 now. So we have a little fish below the surface of a lake. The critical angle is 49. So critical angle of the lake is 49. The fish could see the things above the water surface within the angular range. So we can very clearly tell that if this angle is 49, it should be a 49, and it should be a 49 also. So the total angular range is 98 degree. So it should be the solution. Okay. Now look into the question number 42. Here we have a cylindrical rod. And this cylindrical rod is made up of glass. Its refractive index is 2 by root 3. It is surrounded by the air medium. So air medium is having the refractive index of 1. So angle of incidence is theta. Okay. So obviously light rays are entering from air to glass. So light ray will bend toward the normal. So refracted angle is R. Again it got intercepted by the interface one more time. This time light ray is grazing all along the wall of the rod. So at this point, if you draw the normal, it's going to look like this. So it's the angle of incidence, it's the angle of refraction. So apply the Snell's law 2 times. If you apply the Snell's law for this surface, for this interface, you will be getting a sine theta by sine r equal to n2 by n1, n glass, n1 is 1. If you apply the Snell's law for this surface one more time, this interface one more time, if this angle is r, this should be 90 minus r, is it right? So I can write sine of, here the incident angle is 90 minus r, refracted angle is 90 itself, equal to n2 by n1, n2 is nr, n1 is n glass. So I will be getting a sine of 90 minus r equal to 1 by ng. Okay. So try to relate this. If I relate this quantities, what I will be having? Sin 90 minus theta can be written as cos theta, or so cos of r equal to 1 by ng. So how can we fuse these two quantities together? Let me try to replace the sin r with this following identity. Sin theta by sin r is equal to ng, right? Sin r can be rewritten in terms of cos r. How can we write that? 1 minus cos squared r equal to sin square r. So sin r can be replaced with this quantity. So sin theta by root of 1 minus cos square r means 1 by n square. Okay. On simplifying this, what value will be having? Sin theta equal to root of ng square minus 1 by ng into ng. Okay, ng square, sorry. If I take the ng squared outside, I'll be having like root of ng square minus 1 ng by ng. It will get cancelled off, which is equal to sine theta. So theta equal to sine inverse of this. We know the ng value. Ng is equal to 2 by root 3. So ng square equal to 4 by 3. So ng squared minus 1. ng squared minus 1 is equal to 4 by 3 minus 1, which is equal to 1 by 3 itself. So I'll be getting a sine inverse of ng squared minus 1 equal to 1 by 3. So root of ng squared minus 1 equal to 1 by root 3. So I'll be getting a 1 by root 3. Theta equal to sine inverse of 1 by root 3. That should be the answer. So thank you all.